Hi, everybody, and welcome to our very first third Thursday science webinar for the European Marine Board. It is just 1 o'clock, and I see that we've still got people coming in. So at the moment, I think we have about 40 participants, and we have at least 100 people who signed up. So I'm sure we will have people arriving. But in the meantime, I will start because we've only got an hour. For those of you who don't know me, I'm Sheila Heymans. I'm the Executive Director of the European Marine Board. And we decided to do this webinar series on the science behind our publications, because a lot of work goes into these publications, a lot of science gets accumulated into these publications, but we don't always have the time to discuss the science in detail. So this will be a way for the scientists who've put their effort and time into writing these publications to actually, give us an update on the science that went into it, give us a little bit more detail. These will be once a month on the third Thursday of every month between 1 and 2 o'clock Brussels time, and you can keep up to date with the next ones at the website that you can see there. So if we move along, just some housekeeping rules. Please make sure that your name is clearly entered, so you can change your name. I think on the screen. So please change your name so that we can see who you are when you're asking a question, so we know who the question comes from. The way it works is that you write your questions in the question and answer tab, and then once the speakers have spoken, then I will read out the questions, and I might bring some questions together because it makes more sense for them to be together. If you have any technical questions, any technical support questions, please use the chat function, and one of the team who are behind the scenes will help us to help you with that. For those of you online, please note that the webinar is being recorded, so make sure that any questions you ask is recording relevant. We will be making this available on our website and on the European Marine Board YouTube channel. So for people who can't see it live, they can always watch it later. So the focus of this very first third Thursday webinar is on the science behind the European Marine Board Future Science Brief number 4, which is on enhancing Europe's capability in marine ecosystem modeling for societal benefit. We decided to start with this one because it's something I know something about. And I thought it would be good to start off and train ourselves on something that's a little bit more familiar to me. So the title of today's seminar, where we have 2 speakers, is how can we use ecosystem models to address the ecological and economic effects of climate change and the landings obligation of the common fisheries policy. If you are interested in the document and you don't have it, you can download it at the link below or on our website. So in this document, we actually had a main conclusion that there is no single model that can answer all questions, but that several models can and should be assembled to reach a full end-to-end spectrum. When I say no single model, I also mean no single algorithm, no single package. And so in this case, we're actually going to be looking at one of the packages that was highlighted in this document, but be aware that there's actually quite a lot of other ecosystem modeling software and methods and formulas out there that can and should be used. And we're only going to be looking at one of these today because you can't really discuss all of this in an hour. So we're going to look in detail at 2 publications that's in this that's highlighted in this document. We also came up with some research and development needs for ecosystem modeling in that document, which I just quickly want to highlight. And it's also important to realize that even though we're talking about modeling here, it's also linked to all the other things that's done at the Marine Board level. Obviously, without observations and data, these models are not able to reproduce the reality. So we really need to link with observations and data. There's also new information coming online, eDNA. We need to be able to model adaptation and plasticity, for instance. That's something that we haven't been very good at yet with ecosystem modeling. We have to be able to model biodiversity and ecosystem services. We need to really link up with the best concept and make sure that we do that properly. We also need to be able to model changes in behavior, which is really quite hard to do. And with climate change, that is going to be even harder. We need to be able to reduce uncertainty in our forecasting. That's something that really needs to be with the digital twin for the ocean, for instance, is going to be really important. And then applying machine learning is also something that was highlighted that is needed in the future. So those are the R&D needs that we came up with. And if you want to know anything more, then please do read that document. So as I said, we have two speakers. The first is Dr. Natalia Serpetti. She is a researcher at the Scottish Association for Marine Science in the UK. And she is going to be giving us a talk on her paper in Nature Scientific Reports on the impact of ocean warming on sustainable fisheries management to inform the ecosystem approach to fisheries. This document, this paper was highlighted in the EMB Future Science Brief. And so she's going to give us the background to that science. And then the second speaker is Dr. Igor Celic, who is a researcher at the National Institute of Oceanography and Applied Geophysics in Italy. And he is going to be giving us the details on his paper on the ecological and economic effects of the landings obligation evaluated using a quantitative ecosystem approach in the Mediterranean. So we're going to be talking about the west coast of Scotland and the Mediterranean today. Just quickly then, the next third Thursday science webinar will be on the 17th of September, and it will be by Professor Ferdinando Buero also from Italy. We've got 3 Italian speakers. They're really keen. And so just so you can put that in your diary for now. So without further ado, I think that's all I have to say. So first, I would like to introduce Natalia. Natalia, if you can put your video on, that'd be great. And if you can share your screen, I will stop sharing my screen first, and then you can share your screen, and that'd be great. Thanks. And maybe you want to say something, Natalia, so we can hear you.
Yes.
Thank you. And can you make it full screen? Perfect.
Okay.
Thank you very much.
Thank you, Sheila, for the introduction.
Your 15 minutes starts now.
Okay. Today I'm here to talk about a paper that we published in October 2017 about the impact of ocean warming and sustainable fisheries management. Some information about the past and the present. Then the increase of the world population amplified the human impact on the environment, and to provide space, food and resources in a sustainable way into the future is without a question one of the large serious challenges for our generations. In this context, the number of overfished stocks around the world has tripled. FAO recently stated that 1/3 of the assessed fisheries worldwide have pushed beyond their biological limit. Moreover, we have the problem of biocatches, of catches, of unwanted loss of invertebrates, fish that they are not commercially important, and top predator. Something about the future. Fishing-induced ecosystem changes often occur in regions already impacted by changing environment conditions, under the influence of natural climate variability, but also climate change effect. So the management is getting even more challenging. Fisheries and climate change are generally assessed over short and long time scale, respectively. So, however, this pressure can occur at the same time, and it's important to untangling the conflict on the synergies for management. Here in this paper, we use EWE, which is EcoPath with EcoSIMS modeling approach. And the model I worked on is on the west coast of Scotland on the continental shelves. Just to give you a quick background of EcoPath with EcoSIMS, is a food web modeling where we have functional group of species, they are eating each other. And so they are changing of abundances of biomasses of the species will have a predation pressure of the prey and they have their own predator. So every changes due to the environment, to the fishery cascade in the food web somehow to reach a new equilibrium. This model, a 43 functional group of species that are eating each other, from phytoplankton all the way up to the food web to top predator, mammals, seabirds, seals, dolphins, and whales. And you can also see on the right panel some writing in blue where they represent the fisheries. So fisheries basically in this food web is like a top predator, then take biomass out of the ecosystem. This model was created in 2005 and it was updated several times over the year, and it has been already updated since this paper was published. Some fact about this ecosystem: since the last 30 years, UK landings of all demersal decreased due to a reduction of fishing mortality for all demersal species, partly designed to protect cod that is overfished. So UK decided to reduce the fishing mortality over the demersal species to help cod to recover. Since 2000, in this low fishing mortality environment, however, saithe and aches have thrived, and the other gadoids like cod and whiting and pelagic species like herring continue to decrease. Why? Is because saithe and aches are strong predators of other gadoid and pelagic species respectively. So it's important to consider predation pressure and competition for fishing management policy. And the question I had is, could the warming climate contributed to this increase of saithe and ache in these ecosystems? And the answer is probably yes, because these two species are very tolerant to warming environment, while cod and haddock, they are cold water species and they suffer where this ecosystem is getting too warm. Let's have a look before going into the models, how the temperature change over time in this ecosystem. And here you can see the Atlantic multidecadal oscillation, AMO, on the left, and in the graph is represented by the black color lines. The AMO is a natural variability of the planet, so it's conservative, and this plot shows the trend since 1850. And you can see then you have strong oscillations, positive and negative phase, and change the phase every 30 years. And this is a property of the planet, and they represent an anomaly of the temperature due to unnatural variability. On the left side, on the right side, you can see the sea surface temperature, SST, again from the 1850 all the way to today, which is represented by the blue dot and the blue line. The overall trend of the surface temperature is increasing over this long time. However, it increased oscillating. So I fitted a blue line through the dots, and you can see then the temperature is increased, but it also oscillating in phase with the AMO. That means that when the AMO is positive, the temperature is increasing faster, and when it's negative, it's increasing slower. Then we can make prediction for the future. And for the AMO, we predict future in a conservative way. So we mirrored the behavior of the AMO in the past, all the way up to the end of the centuries. And for the sea surface temperature, we use IPCC scenarios at the different rate of CO2 emission. So we have a rate of 4.5 on the green, and on the 8.5 on with the red line and dot. We can see again, and I made this prediction for the future, carry on applying the phase of the AMO. So there are, when, especially at the 8.5, when the AMO is in phase with the rising temperature, we have a very strong and quick increase after the 2050. But how the species respond to these changes? Then in these graphs, which is one of the main figures of the paper, you can see the species in the group, in the model. Then they are ranked by cold water species, herring, cod, haddock, all the way up to warm water species, more tolerant, like horse mackerel, and ache. This function, they are Gaussian function that represent the response function to temperature. So we have cold water species, they have an optimum in this case, as an example, around 5, and their optimum condition decrease when we move away from the optimum conditions. And warm water species, optimum temperature around 15, and again, a decrease of this optimum condition, which in the model are represented by a consumption rates, which is in the formula, is represented in this formula. So if the water temperature in this example is at 10 degrees, we can calculate a scaling factor, then decrease the consumption rates of these species based of their optimum condition and the water temperature. So then in these results, this might be too technical, but what we've done we fit the model to observation of biomass and catches driven by surface temperature and fish mortality. And we estimated a primary production anomalies called, which is a function that better explain the fitting of this model. So it's basically a function that is calculated by the software. However, after this function has been calculated, we looked at correlation of this anomaly of function then could represent something that is actually real in the ecosystem. And this function was correlated with the AMO in the environment, which means then basically the AMO have a strong impact on this ecosystem to drive the distributions or the temporal trend of the species. This has been found in other paper and also in the Pacific decadal oscillation have a strong impact in other ecosystems. So the natural variability of the planet has an impact on this ecosystem. Then we look at the future, and as I said before, we use IPCC prediction under different rates of CO2 emission, 2.6, 4.5, 6, and 8.5. And then I used this rate of increasing to apply to the ecosystem in my model. Replicate the natural variability and also apply the oscillation of the Atlantic multidecadal oscillation on these predictions, as explained before. The driver in this ecosystem is not just the environment, it is also the fisheries. Fisheries are a strong driver in this ecosystem, and here we use scenarios of two types of fisheries. When the fish's mortality is calculated as the status quo, so the model ends in 2013, and we predict the future at the fish mortality set at 2013. However, some of our stock, as I said before, they are overfished or they are decreasing. So I also apply a fish mortality device by the stock assessment. And you can see here a table, just to give you an example. Cod status quo have a high fish mortality, while at the stock assessment, that a device to be fished much more. On the opposite, we have SAIT, then is basically not fished at the status quo because we don't have quota or UK is not interested to it. But because the population of SAIT is so large, we could actually fish it way higher rates. So if we are higher rates of fish mortality at the stock assessment device. Then when we apply an MSY, maximum sustainable yield device fishing mortality, we can make some cod and whiting stocks recover, and I apply the impact of climate change on them to make it more visible the impact on an healthy stock. So some results. Here you can see then gray seals, for instance, have been increasing over the last 30 years, will continue of increase a status quo. However, at the MSY, they decrease because we are fishing their prey. So the fisheries and the top predator gray seals, they are in competition with the prey. However, gray seals don't like warming scenarios, so they all decrease in all these scenarios. SAIT, as I said before, on the last 30 years, increase of 4 times. At the status quo, it stays stable, but at the MSY, it decreased because we are fishing way more than at the status quo. However, if you look at the line of the color line for the warming scenarios, there are not much difference. That means that safe is very tolerant to change or warming water. Herring has exactly the opposite trend, is a cold water species. It has been declined for the last 30 years. And as soon we apply the warming scenarios, this species is basically disappearing. Haddock is a cold water species again. Under the MSY scenario, which is the dashed line, we can see that the stock recover, but as soon as we apply the warming scenarios, they decline again. Cod is very sensitive to warming water. It's not happy at all. Under the MSY scenarios increased, but as soon as we use a warming scenarios, the stocks is collapse again. On the other side, whiting is a species that thrive under these climate change scenarios. It thrives for two different reasons. One is because this species is very tolerant to warming water. It's a Lusitanian species that lives in the north of France. So we have a wide distribution in the Northeast Atlantic. So it's very tolerant to warming water. And at the same time, the predation pressure of the species decrease because cod and haddock, then they are predator of whiting, decrease. So the successful recover of whiting is due to a nice environment and low predation pressure environment.
Natalia, you have 2 minutes.
Cool. Well, and now I'm gonna say something about the future. I use a Gaussian shape as I described before, and the standard deviations, and many other paper came out using this function. This function have some limitation because it doesn't take in consideration the physiology of the species. So we can use different shapes, beta shapes, for instance, the one highlighted in dark blue, to define the response functions. Some other authors use a trapezoid shapes, then have very easy to find this data to define the shapes, but it's considering a uniform distribution over a population between the 10th and the 90th percentile of the distributions. Some other modeling approaches calculated a shape of this response function. However, this approach requires lots of data, and we can infer this function to other ecosystems. Others modeling approaches looking at different ecosystems, like in Australia, identify a Gaussian shape with a Gaussian split to calculate the standard deviation the same way I've done it. And the other ones, again, using a different modeling approach, again, find a Gaussian shape with standard split Gaussian standard deviation. On a community level, identified species, they have a narrow thermal range, then of course they are more sensitive to changes. Like, and they also predict in the areas with warming, like the Northeast Atlantic, will shift to a dominance of species that are tolerant to changes. So they also predicted in cod and herring, they will suffer in this ecosystem, while hake, saithe, and other horse mackerel or other migratory species that will be more successful in this warming environment. So for the future, I am testing different shapes from the trapezoid to the Gaussian to the beta versions, and try to predict the sensitivity of the model to these shapes, because shapes in this case for response function to temperature matter, and it's important to assess the sensitivity of our model to identify the best way of making this prediction for fisheries management. Thank you to all my co-author and to all of you for listening, and I'm waiting for questions.
Thank you very much, Natalia. Thanks. You can probably stop sharing your screen if you want.
Yes.
Excellent. Thank you very much, and sorry for giving you the the heave-ho, but I was a bit worried that it was going to go a little bit over. But that's good. I see we have one question, so we'll take that one. It is from Ivan Koneska, And oh, he's got a few questions all of a sudden. People are using the chat instead of the question and answer, but that's okay. I'll use it from there. So he's asking, if I can get to it, can you explain the stability of SAFE at different temperature scenarios, even if their preys are decreasing? If you want to go back to your slide, sorry, you might have to share your screen again.
Okay. Oh, maybe that one. Can you see it again? Probably not.
Not yet, no.
Okay.
You have to pick the right screen.
But I have only one.
Maybe I can share it.
Maybe I've done it now.
Yes, yes, yes. You just need to go to the right slide.
Okay. The question is why state is so stable despite the fact that these sprays are going down.
Yeah.
And that's because the state is very, it's a strong predator, but it's not very selective. Basically, eats whatever is in there. So there is, while there are cod and whiting, they are going down. There will be ache, for instance, that goes down, is going up, and is part of the sprays as well. And if you look also at the tons per square kilometers, the abundances of cod, haddock, they are 0.1, 0.2, 0.3 tons per square kilometers, where sate abundances is very high in comparison. So the reductions is relative lower, the reduction of cod compared to the reduction of herring, then is declining, but is still 2-3 tons per square kilometers in the model. So we need to look at the unit. So sate, it will have less cod to eat, but it will have loss of whiting to eat. So it can switch very easy into different gadoids because his diet, let's say, is quite heterogeneous. And that is why it's more stable than other preys.
Okay, thanks. Sorry, I think somebody, Maciek, said that there's an echo. I just muted myself. I hope that helped. Okay, we have another question also from Ivan saying, what would be the next steps for improving the models? I guess you mentioned that for the temperature. Yeah. But then he asks, what about modeling deep sea communities, current variability with climate change and other nutrients? I'm assuming, I guess, because you didn't go into too much detail, this model doesn't go into the deep sea, right?
No, it's only on the continental shelf. So here is the model domain. On this slide, you can see it. So we are not looking at deep sea community. In this case, there is a deep sea model for the west coast of Scotland, which Sheila made it. And she knows really well that making models from deep sea community is very difficult because model need data. And in the deep sea, we don't have as much data than we have in continental shelves. Of course, if you have enough data, you can build it up a model then well fit to the observations, then you can make a prediction also of changes of nutrients, because of course, in the deep sea, the primary productivity basically sink through, as marine snow, to the deep water. So changing on primary productivity will cascade in this deep sea ecosystem as well. So of course we can, using this modeling approach, you can simulate scenarios where the primary productivity change in the surface and we'll have less food for the benthic community, for instance, in the deep sea. So the future is, what is always been in modeling is try to have as much data as possible, high quality data, and try to have a model that fit observations. And in terms of response function to temperature is exactly what I was trying to very quickly illustrate at the end of my presentation. Then it's important to define this shape of response function to temperature, the one they are more suitable for our ecosystem. There are ecosystems that are made of very temperate species, then they are not changing so much, so they are tolerant to change way more than cold water ecosystem. In the EcoPath model from the Arctic, is even more important because there are species then they are very sensitive to change, and the Arctic is one of the environment that is changing faster than any other. So the future is doing sensitivity tests for important species for the ecosystem, or in my case, herring, cod, haddock. Then they are the one they are suffer more of this variability of warming water, and testing which function represents better that species.
Thank you, Natalia. Okay, and then there was a few other questions. I'm going to just answer Ivan's question. The other part of the question about whether you can use current variability with climate change and other nutrients. The other thing that Natalia didn't mention is that these models in a spatial way can be driven by three-dimensional physical biogeochemical models. And somebody else asked whether you're planning to use EcoSpace, and that's what you would need. You would need the spatial model of the EcoPath suite in order to do that. And then you can look at current variability and other nutrients. Well, other nutrients you can also do in time, as we've done with temperature here. So you can do it there. So there's all these possibilities, but as with any other project, it depends on who's going to be paying for it, I guess.
Yeah.
And then there's a question about how does climate change effects in each different area, but how do you identify the effects? It's from Yashin Chu. Sorry, I'm not doing very well on the pronunciation. So the question is, the effect of climate change in each area should be different, but how do you identify the effect easily and fast? And I guess I'm not sure if she means different areas in the west coast of Scotland or different areas in the world. I don't know if you want to try and answer that one, Natalia.
Yeah, in different areas in the west coast of Scotland, then we need to go into EcoSpace, as you previously mentioned. We can have temperature layers in space, and then you can, if we have an higher resolution EcoSpace, then you can regionally predict changes, even if on a regional scale. That depends on the resolution of your EcoSpace. If you are asking about different in the world, well, the data I showed, they have been extracted for my domain. So there are climate change models. There are many of them. There are ensembles of models for climate change, which is what I used. And I calculate a mean using these ensembles, and I extract that values from a shape file for the west coast of Scotland. So they are extracted for my area. It's not a world average, the one I used.
Okay, thanks, Natalia. And I think that also answered Diego Panzeri's question, whether you're thinking to use EcoSpace to predict movements in species or fisheries based on climate change scenarios. I'm guessing what you're doing already, right?
Yeah, the model in EcoSpace has been already developed and has been coupled. That is what the term we use to say when we use biogeochemical model or hydrodynamic model to drive some elements of our EcoSpace in this case. So the EcoSpace model on the west coast of Scotland is coupled with a NEMO Earth. Then it's basically predict changes on a spatial scale, temporal and spatial scale. And we have simulation now for NEMO ERSEM under IPCC 4.5 and 8.5. So we can make a prediction in space using EcoSpace and this information from NEMO ERSEM, then predict, it's coupled with hydrodynamics. So we have currents and climate change together.
Okay, thank you very much, Natalia. So if anybody has more questions, please use the question and answer like Diego did. But thanks, you can stop sharing now, and then I think we'll go to Igor, and then we can maybe have a little chat afterwards if we have some time. So thank you. You can mute yourself and stop sharing your video, and then Igor, if we can see your face, and perfect, thank you. And do you want to share your screen? So Igor is going to be talking about his paper on the ecological and economic effects, right? So there you go. Thanks, Igor. Your 15 minutes starts now.
Thank you. So I will explain you this the work we did on the on the ecological and economic effects of the landing obligation. And because it was quite a debated topic about the fishing common fishery policy. And I wanted to go that much into details about the technicalities, and I will focus more on the, is it working? Yes, okay, more on the results we obtained. But for the beginning, just a brief recap on what is the discard policy and the regulation. So the discards are an issue in fisheries worldwide, and therefore the reformed common fishery policy includes measures to contrast discarding practices by introducing the landing obligation for unwanted catches of species regulated either by the quota or having minimal conservation reference sizes. It is worth to be noted that the fisheries are regulated by quota in the North Sea and by the effort or technical measures in the Mediterranean and the Black Sea. Preliminary bioeconomic studies criticized the new regulation, made its application in the Mediterranean doubtful, and there are a few ecological studies about it. So we wanted to use the ecosystem approaches to have the ability to account for a broader ecological context, interspecific interactions, and which can be used as a tool for strategic management advices. So in this short summary, I will illustrate you the possible ecological and socioeconomic effects of the landing obligation regulation in the Northeast Adriatic Sea area, use an operational model for fisheries management in the study area, and we will also analyze alternative scenarios and measures that might reduce the unwanted catches. So on this map, you have a representation of the Northeast Adriatic Sea and its properties and fisheries. The modeled area covers around 1,000 square kilometers and includes Slovenia and one region in Italy. Our study is based on starts in 2005, when there were 681 registered fishing vessels divided in 6 fishing categories. You can see them in the different colors and in the bottom left. And these colors will help you to identify the different fishing gears throughout the presentation. And on the map, you can see the usual fishing areas they use. So in 2005, the Northeast Adriatic Sea fishery landings and discards amounted approximately to 7,000 tons each, of which approximately 13% of the discards was subject to landing obligation regulation. And most of it is coming from the auto trawlers, as you can see with the red fish. These fishes will help you during the presentation, indicated in green or big fish, the commercial catches. The red or the small fishes are the unwanted catches, and gray fishes are the other discards. So again, the same as Natalie, we used an EcoPath and with EcoSim model suite to conduct this study. And the food web model is composed of 33 functional groups and 10 fishing fleets and 1 aquaculture activity. A little detail for you is that we used cubic length overall for trolling vessels as a primary index of fishing capacity, and while for the other fishing gears, we used the number of fishing vessels because their fishing gear didn't change that much based on the size of the vessel. So the landing obligation was studied by comparing the status quo scenario where all unwanted catches are discarded back to the sea and recycled by the food web, with the landing obligation scenario where the unwanted catches subject to regulation are exported from the ecosystem, are landed for non-human consumption, and are sold for fish meal at 0.20 euro per kilogram. And here you can have, you can see our first results. So we have on on this plot represents the functional groups of biomass difference between the two scenarios expressed in percentages. And you can see on the bottom that there is a reduction of about 11% of the discards in the sea, which caused reduced resources for scavengers and their decreased in their biomass. And this created the cascading effects up to the top predators who decreased their biomasses, but these effects had some positive effects on other functional groups because it reduced their predators. So the reduction of biomasses that we observed had a negative impact on marketable landings, decreased by approximately 0.4%. On the other hand, the regulation increased significantly the landings of all fishing fleets except the rapido trawlers and dredges. The largest impact was on the otter trawlers, who doubled their landings. Overall, the total landings increased by 13%. The reduction of marketable landings reduced also the revenues from the marketable species in all fishing fleets by approximately 0.5%. However, the large increase in total landings is not replicated for total revenues. Overall, the changes are small, and the only increase in revenues is observed for revenues in otter trawlers, but it's not that much, so the fishermen might not be that happy because they have, remember, to work double right now. So what makes fishermen happy? In essence, to have more resources, to work less, to have less processing, and earn more. So how does the landing obligation perform on this scale of happiness? Well, not so well. In a nutshell, it slightly reduces the biomasses at sea, it significantly increases the workload, and it has no economic benefits and anyway reduces the marketable revenues. Therefore, we test several different alternative scenarios to mitigate the adverse effects of the landing obligation and compare them with the status quo scenario. We will assess them based on the pressure on the environment as the changes in the unwanted catches and the changes in and the economic benefits as changes in marketable revenues. So an effective measure results in reducing the unwanted catches more than the marketable revenues, staying above the identity line and in the green area. If the changes in the catches and the revenues are proportional, moving along the identity line, our measure is ineffective because it regulates the fishing effort and doesn't change the properties of the fisheries. A bad measure has negative effects on the environment and it damages the economy, and we are deep into the red area. As we saw earlier, the landing obligation makes small overall changes as indicated by the big black dot, which is in the center. And there are small changes also for all the fishing gears. The alternative scenarios are based on different measures that change the fishing effort, the fishing gear, or introduce the quotas. Additional estimation of the scenario's performance were assessed using 3 indicators: the resources at the sea, the employment, and the revenues, which you can see, you can follow in the bottom right of your screen. So the first scenario proposes an introduction of quotas for small pelagic fishery. While the 2 target fishing gears catching small pelagic show effort reduction effects, the overall performance of the scenario introduces small changes. Positive effects are observed by increasing the resources and maintaining the employment, while the revenues are slightly reduced. The second scenario halves the fishing effort of the otter trawlers. Remember, the fishing gear contributing the most to the unwanted catches. This measure almost halves both the unwanted catches and the revenues for the target gear and increases the resources at the sea, but with some mixed effects on other fishing gears. Overall, the scenario performs quite well in reaching the green area, but halving the employment might be socially unacceptable. So in the third scenario, we tested the selectivity of the trolling fishing gears and improved it. It produced positive changes for auto trawlers by mainly reducing the unwanted catches with minor reduction to their revenues. However, the rapido troll wasn't affected because it has different catch composition and little species subject to the landing obligation. Overall, this scenario reduces the unwanted catches without sacrificing the revenues and has positive effects on increasing the resources, maintaining both the employment and the revenues. In the last scenario, has both quotas for small pelagics and improvement of the trolling gear. So it's a combination of the scenario A and C. The effects are similar to the previous scenario, while adding the effects of the quotas to the small pelagic fishery. The overall performance is similar with a slight reduction in economy, but resources are increased even more. So to wrap up this analysis we conducted, thanks to the ecosystem approach, we identified both the direct and the indirect effects. Top predators suffered the most due to the regulation and mainly the marine birds. The regulation increases the workload, reduces the biomasses at sea, reduces the revenues, and landing the unwanted catches will not compensate economic losses. So we have a sad fisherman. The combination of improving the fishing gear selectivity and applying quotas result as a suitable alternative, but none of the adaptation scenario compensated the adverse effects of the landing obligation. The landing obligation has negative ecological and economic effects in systems where fisheries are not regulated by the quota, such as the Mediterranean Sea. And finally, I'd like to point out that these results were also presented to a group of fishermen in Italy who were delighted by the holistic approach of our work and find the results representative of their experience and the situation they observed. So more detail can be found in our paper, and we would like to acknowledge also the colleagues that gave us their contribution and the projects RITMARE, FIMAPS, Mantis, and the Copernicus for the support. So thank you very much.
Thank you very much. Thank you very much, Igor. So any questions for Igor? There were lots of questions for Natalia, but there doesn't seem to be any for you. Maybe you have answered them all. I have a question though. I'll start off. So in your scenario C, you said you improved the troll selectivity. How did you do that?
We changed the selectivity by changing the composition of the catches and discards in EcoPath. So we actually, in a technical way, we created additional dummy fleets, and by modulating the fishing effort, we shut down the fleet that had, let's say, the less selectivity, and then we gradually increased the fishing effort of the fleets with better selectivity. So it was a gradual transition between them. To do this, we had to think in advance and set up the whole EcoPath model so that we created these dummy fleets in EcoPath, but with very, very low catches or discards, so they don't impact the fitting and the initial scenarios and simulations.
Yeah.
And
I think my question is more, how does it relate to the real world? Are you assuming that in that case, the fisherman would use a different size net or something like that?
Okay, sorry.
That's what I'm getting at, not the technicality.
Yes, I'm sorry. Yes, so we based this improvement on the studies by putting in action the squared mesh of 40 millimeters instead of the diamond 50 millimeter mesh. So yeah, we used the studies that were conducted in the Adriatic, and based on these studies, we implemented them in EcoPat. So this is the, um, the work we did, and we did it for the trolling otter trawlers and the rapido trawlers.
Thanks. And then following on from that, an anonymous attendee has asked, were the selectivity changes allowable under the current EU technical regulations? I don't know.
Well, I mean, this selectivity is already in place. I mean, the fishermen are have a free will to choose whether they wish to use a diamond 50 millimeter mesh or a 40 millimeter square mesh. So it's up to them. Both of them are legal, and they are inside the European Common Fishery Policy. But the square mesh has a better selectivity.
And by better selectivity, you mean that it catches bigger fish, not such small.
Yes, it passes through the
smaller fishes
and the unwanted catches.
Yeah, thanks. Okay, I don't know if there's any other questions. Otherwise, I will keep on asking.
I would like also to add, if I can.
Yes, please do.
We conducted this study also taking into account the uncertainty, because we used an ensemble of models, and we used actually 21 ecosystem models, each of them slightly different because each of them was calibrated in a different way, and they have different vulnerability settings, because we wanted to test the fitting for different functional groups. So there is the variability of the diets. If you let me pass this metaphor, is accounted in the model. So the model takes into account that in some cases other groups are better fitted than the others, but there is an interaction between them.
Okay, thank you very much. I'm still not seeing any other questions. I guess my question was more about when I heard the first time about the landings obligation and the fact that you had to bring all of the fish to the shore. My first gut feeling was, what is that going to do to the benthic community? And I guess your data showed that to some extent, didn't it? The things that eat the dead fish on the bottom of the ground, sure, seabirds would definitely be affected, but other things that eat a lot of discards. And I wasn't, you didn't really go into that into too much detail, but was there some of that? Did you see some of that? I can see the reducers in elasmobranchs and flatfish and stuff like that, which would be due to the fact that you've taken this food out of the ecosystem, right?
Yes. For example, if you can still see my screen.
Yes. Yes.
Okay. So if you watch, for example, the gastropods and the decapods, there is a nice effect on the benthic community. The decapods are primarily scavengers, and so they have the negative effects, and their biomass decreases. Gastropods are also scavengers, but here is a nice catch, because the decapods are also predating on the gastropods. So the reduction in the food intake due to reduced discards is mitigated by a reduced by reduced predation. And generally, in our model, we have a strong bottom-up effect and a strong detritus cycle. So we have a strong input from the scavengers and from all the fish functional groups that use detritus and the discards to recycle them into the ecosystem. So we have negative effects on them, and they are the ones that primarily exhibit them. However, others are have mixed effects because they are either based on filtrating as filtrating benthic invertebrates and or mass or bivalves, and so it's quite complex. It's not straightforward. It depends. It depends on who is more connected to this detritus cycle.
Thank you very much. Okay, I think we're just nearly at the end of our hour. I don't know if there's any other questions for either Igor or Natalia. Natalia, do you want to stop sharing your screen there, Igor? That'd be great. And then Natalia, if you want to put your video on. I guess and Igor, keep your video on as well. Stop sharing your screen, but keep your face on the screen. That'd be great. Can you do that? Okay, excellent. So thank you very much. I guess this was very very intense and very fisheries focused, I guess, for the Marine Board participants. But I guess I wanted to just see if you have any feeling for what you think the usefulness was of I guess you didn't really necessarily directly work on the document, but do you think that it's useful to have such a policy brief or policy document for, you know, using it in your papers or in your grant applications or something like that? Do you think that's it has any use? And maybe it's a really unfair question because maybe you think it doesn't and you don't want to tell me.
Well, I give the answer. In my case, I think it's very useful. And I think in science generally is very useful because it reaches a completely different audience of the one open a journal and read our science. We generally are too specific. We are going to too many scientific details, and normally that push away the people. Then they're not doing our job, and it's a limitation we always had. We don't reach the right audience, and we are not. But however, management, fisheries, what stakeholders they're people that are not reading our science that way. So we need to reach different audience.
Yeah.
So these documents are very useful. So this presentation then we are doing.
Yeah, thank you.
I think it's very useful because ecosystem models are quite complex. As Natalie said, there is a lot of data, and it's difficult to present all these results and the data in a comprehensible way for somebody that, even for scientists, it's difficult, even less for let's say non-technical people or people that are not involved in fisheries. So for me, searching ways for communicating this result in a simple way, understandable way for common people is a way to go, because they will probably appreciate much more the work we are doing, and it will be much closer to them. We will reach the people we need.
Yeah, thanks. I see there's another comment from Ivan saying that the next steps would be add or to merge environmental changes like climate change. I'm assuming it's climate change, CC, not carbon capture, into this model. I guess we've done that already in the west coast of Scotland with Natalia's, and I don't know if you guys did that, Igor, if you had any climate drivers to your models. The time frame was relatively shorter, I guess.
No, at the moment we don't have the climate drivers. We are now creating a new model of the Adriatic and the Ionian, and it will be much larger, of course, and we will have all the biogeochemical drivers in it, and probably we will also focus on the different IPCC scenarios.
Yeah, yeah. So for Ivan, I guess in the document that we wrote in the policy future science brief, we basically advocate that that's what you have to do. You have to incorporate all of the drivers in order to get the models, and it's better if you use an ensemble of drivers on an ensemble of biogeochemistry models, and then on an ensemble of food web models. So in this case, we really only spoke about EcoPath with EcoSim, but there are many other, there's more than one way to skin a cat type of thing. So there's other models out there that can actually look at the ecosystem from a different aspect. And what we've done in other projects, what other people have done in other projects, is looking at how do you combine these, like the IPCC does. How do you do that in a kind of ecosystem modeling context? And that's definitely something that is something to be looked at into the future. So we will definitely be looking at that, and it is definitely one of the recommendations that we have in the future science brief. So I think we've just gone over time. There's also comments saying thank you very much. It was great to have it. So I think with that, I will close and just remind you that our next talk will be on the 17th of September, and it will be talking about the cells of ecosystem functioning towards a holistic vision for marine space by Professor Nanda Boro. So I'll look forward to seeing you guys at the third Thursday webinar. Third Thursday science webinar. And thank you very much to Natalia, who took off from a holiday, and to Igor, who has been giving us great talks. Thank you very much. Bye.
Inviting us. Bye.